Alright, in this video we're going to describe and define simple harmonic motion. So we'll call it describing and defining simple harmonic motion. Okay, so what we're going to do is we're going to observe a pendulum. Completing an oscillation. We're going to describe its motion in terms of its position, its velocity, and its acceleration. And then we're going to define simple harmonic motion in terms of position x and acceleration a. So ultimately we're going to end up with a clear definition of what simple harmonic motion is. So those are our aims for this session. So I'm going to zoom in a bit so I have a bit more space to write underneath here, and then we'll go through and we'll have a look at what this pendulum swinging looks like. So here we have a pendulum bob down here, and it's attached to a string which extends up further than the video goes. And this video starts as it's swinging through its middle position heading to the right. And remember, we're going to use the convention that to the right of equilibrium is positive, or anything pointing to the right is positive, and anything pointing to the left is negative. And in this video also, because this point is tracked, it's going to tell us what the acceleration and the velocity is. The acceleration will be represented by a blue arrow and the velocity by a red arrow. So let's have a look. So it's swinging out towards the right, in the positive direction. We can see its velocity is decreasing and its acceleration is increasing. And then it turns around and heads back, and its velocity is now increasing, and its acceleration is getting smaller and smaller, and at equilibrium it has no acceleration. And then as it swings out to the left, it's slowing down again, so its acceleration is to the right. Its velocity decreases until it reaches its maximum position where the velocity is 0, and then it swings back to its original position, acceleration getting smaller and velocity getting bigger. Okay, so that's what we're going to describe. And we're going to focus on those three key positions. So we're going to look at describing simple harmonic motion now. And we'll do that. We'll underline that as well. And we're going to focus on three positions. So we're going to have when it's the furthest it's ever going to be to the left. And then we'll look at when it's at equilibrium. When it's at its equilibrium position, so it's not recognizing that as a circle. In fact, I'll just copy this one. And I'll pop it there. And then I'll pop one here. So, and I'll just screw this one up so that they're all in line. Okay, so we're going to look at these three positions. So we're going to start in the middle, just like the video does. So we'll call this position 1. And we'll call this position 2. And position 1 is when it's heading that way. And then position 3 is when it's coming back this way. And then position 4 will be when it's reached this maximum position. Okay, so we'll look first at position 1. And what we want to do is describe the position, the velocity, and the acceleration at each point. So at position 1, we have, I'm just going to go back to the start here and then go forward one frame, and we can see that we have a very big positive velocity, so a velocity pointing to the right, and 0 displacement and no acceleration. So at position 1, x equals 0, v equals big and positive, and a equals 0. Alright, as it swings out now towards its maximum position, we can see the acceleration is getting bigger, and it's slowing it down because it's in the opposite direction to the velocity. And the velocity is getting smaller, and when it reaches its extreme position here, I went just one frame too far, when it reaches its end position, momentarily it's not moving, so the velocity is 0 at that end position. The acceleration is really big and pointing to the left, and the displacement is really far to the right of equilibrium. So we can say at position 2, we can say x is big and positive, and v is 0, and a is big and negative. So we can see that the acceleration is in the opposite direction to the displacement. And it seems to be doing the same thing. So it's getting big when the displacement is big. So let's look at what happens at position 3. So it's just hopped one frame too far here. So at position 3 we can see that it's in its equilibrium position, so the displacement is 0. The velocity is now really big, but in the opposite direction, so it's towards the left, and the acceleration is also 0. So at position 3, because we're at equilibrium, x is 0, v is big and negative, and a is also 0. So it looks like x and a are both 0 at the same point, both in the first position and in the third position, which makes sense because at equilibrium the net force should be 0, so the acceleration should be 0. Okay, if we let it play and we go out to the final position, you can see the velocity is decreasing again and the acceleration is increasing in the opposite direction. So now we've reached the far left position, which means the displacement is big and negative. The acceleration we can see is now really big and pointing to the right, so it's big and positive, and the velocity is now 0. So at position 4 we can see that x is big and negative, sorry. We can see that the velocity is 0 because it's not moving, and the acceleration is big and positive. Okay, so now we can see a kind of pattern here that whenever x is big, a is also big, but they always have the opposite sign here. So we can see that when this one is positive, this one is negative, and when this one is negative, this one is positive. So they're kind of both doing the same thing, getting big at the same time, but they have opposite signs. So we can draw that as a kind of graph. I'm just going to sketch a graph here. I'm not going to bother with the ruler. So if we draw a graph of acceleration against position, so this will be in meters per second squared, and this will be in meters, we can see that when a is big and positive, which it was here in position 4, x was big and negative. So when a is big and positive, x is big and negative, which means we can put a point here. When x is 0, so at position 1 and position 3, we can see that when x is 0, a is also 0. When x is 0, a is also 0. So we can see that at this position, they're both 0. And at this position, x is big and positive, which was position 2 here, and a was big and negative. So our final point goes there. And now we haven't really proved this, but I will in a moment. The relationship here is a straight line relationship. In other words, the acceleration is proportional to the displacement. So if we double the displacement, the acceleration will also double. We can show that here using this tracking software. So I'm going to add a graph here. So this is a graph of acceleration versus displacement, and we can see here 0, 0, the line cuts through 0, 0, and it is a straight line. It's got a few squiggles because the tracking isn't perfect, but basically this is a straight line. So whenever it's really far from equilibrium in the positive direction, the acceleration is really big and negative, and as the displacement decreases, so does the acceleration by the same proportion. And when the displacement is really big and negative, the acceleration is really big and positive, and that's the position that it's sitting in at the moment. We have a big negative displacement and therefore a big positive acceleration. Okay, so this is a graph of this graph. We could write an equation for the graph, basically y equals mx plus c. We can see the y-intercept here is 0. It has some constant gradient, so we can write our y value, which is a, is equal to some negative constant times x. I'm just going to add a little comment here about just what this constant is. It's going to depend on how quickly the motion is repeating. And the reason it does is if it's repeating more quickly, then the acceleration has got to be bigger. So this constant here depends on the frequency of the motion. So I'm going to define this constant, and we'll explain a little bit more about why it's defined as this later on. But the constant, so this constant depends on the frequency. And it's defined as constant equals something called omega squared, where omega is equal to 2 pi times f, or omega equals 2 pi over the time period. And it's measured in radians per second. So basically, if we want to write out this equation the way that it is in your notes, we can say that the acceleration is equal to negative omega squared times x. And this is useful to know because now we can relate the acceleration to the displacement by just multiplying the displacement by 2 pi divided by the time period squared. And the way that we write this in words, and this is the definition of simple harmonic motion, the way that we would write that is, in order for something to be simple harmonic motion, for a motion to be SHM, the following conditions have to be met. So we have to have acceleration is proportional to displacement from equilibrium, and so that's condition 1. The second condition is the acceleration is in the opposite direction to the displacement. Okay, if those two conditions are met by any object, then that object is undergoing simple harmonic motion. So that's our definition of simple harmonic motion.